All right. Well, hello, everyone. Thank you for joining us for the 2025 ISAR Virtuaeolian seminar series. The entire ISAR board is excited to continue this Virtuaeolian tradition. And before I turn it over to JB to introduce our speaker today and the winner of the ISAR Career Award for 2025, just want to give you some general information about the structure of today's talk. So please keep your microphones off unless called on in the Q&A after the talk. Please feel free to type your questions in the chat at any time, but we're going to wait till the end to read them aloud. During the Q&A, again, also you can hit the raise your hand button if you'd like to just ask your question out loud. This meeting is being recorded and will be shared with the ISAR community. Please hang with us until the very end because we also have some important updates to share. And lastly, we ask that everyone contribute to creating and maintaining a welcoming, respectful working environment that fosters diversity, inclusion, and belonging. And so now with that, I'll turn it over to JB. Thank you.
Okay, thanks, Maddie. I have the pleasure to introduce Dr. Yaping Shao to you. Yaping is a professor in meteorology at the University of Cologne in Germany. And already since the 1990s, he has been working on dust research. He's very well known for his book, Physics and Modeling of Wind Erosion. And actually this book documents the progress in Aeolian research already since Bagnall's work in the 1940s. Yaping has made many contributions to the field, which include, this is far from complete, but he worked on mechanisms for dust emission, threshold, the famous threshold friction scheme is an impossible word for me to pronounce as Dutch, threshold friction scheme. Anyways, physics-based dust and emission scheme and integrated dust modeling systems, and of course the famous dust cycle concept. Yaping has published more than 165 papers and counting, and he's actually listed in the top 2% of the scientists in the Stanford University database. Presently, and since 2023, he is the leader of the HESCORE initiative, which stands for Human and Earth System Coupled Research, which explores a new research territory in which they try to integrate natural and humanity sciences to study cultural evolution in a changing climate. Well, from this very incomplete summary, it's already very clear that Yaping is an outstanding candidate for the ISAR Distinguished Career Award, and the committee did not have a hard time to award it to him. And we are very happy that his nominators, Martina Klose, Gil Bergametti, Gilles Bergametti, I should say, Ning Huang, and Masahide Ishizuka, nominated him, for which we thank you all. Well, last week, Martina and I had the pleasure to actually hand over the award to Yaping, which came as a surprise for him. He knew he had the award, but he didn't know we were coming to give it to him. And we would like to share a little video clip of this happening with you. And I hope this works if I press the next button. Here we go.
You should share your screen, JB, first.
Congratulations once again. Thank you. Big honor for me to be allowed to hand over to you. Thank you all to
it was
Martina.
More than a pleasure to nominate you. Also from my...
Sorry, it doesn't work. Philip, don't you see anything? Oh, Maddie has a thumbs up, so...
Okay, I don't see it.
There you go. Thank you. Big honor for me to be allowed to hand over to you. Thank you all to
it was
Martina.
More than a pleasure to nominate you. Also from my personal perspective, I think you have more than deserved this prize. So.
This is a prize from friends, so he's very honored. So I must say I never received any prize.
Really?
This is the only prize I received, but from friends. Okay, thanks very much.
As you can see, it was a very happy occasion, and we had a lot of fun handing over this award to him. So without any further more disturbing news from my house or from me, I would like to give the floor to Yaping, and I will stop sharing, and then maybe Yaping, you can start sharing.
Okay, can you hear me now?
We hear you, and we see you haven't started the presentation yet, I think.
Okay, I haven't started presentation yet. Yeah, so now it should start. All right, okay.
Yaping, you still haven't started the presentation. It's still presentation mode, at least in my screen.
This is.
I can see your screen, but it is still in presenter mode. And here it looks like if you swap the display settings, we're seeing the presenter side. Towards the top of this view where it says display settings, Yaping, I think you need to just switch the views.
Is that?
Yes,
correct?
looks good. Perfect.
Okay, sorry about this. Okay.
No, it's okay. Thank you.
Okay. Thanks to Jan Berendt, Bettline, and Philip for organizing this event. I'm deeply grateful to the selection committee for their trust, and especially touched, as Jan Berendt already said, by the effort that he and Martina made to come a long way to present this award to me in person. The collegial warmth is really remarkable. And my sincere thanks to Martina, Jie, Ning Huang, Jie Zhang, and Masahide for the nomination. Over the years of my involvement in Aeolian research, I've had the privilege of working with a long list of wonderful colleagues. I feel really very fortunate to be part of the community. Okay, thanks very much. So today I'll be talking about modeling source limited distribution. So this is actually a topic we are, I think everybody, all of us are talking about and thinking about it. It has also been in my mind for a long time. And recently I did a little bit of work, so I would like to share the results with you. So, but maybe I start with this photograph. This is from a paper I wrote with a number of colleagues listed here, a tribute to Mike Ropak for his contribution to Aeolian fluid dynamics. So when I graduated in 1991, I joined the group of Mike Ropak in CSIRO. And this is a photo of Australian Aeolian researchers gathered at the Murdoch University in Perth to stage the first Australian workshop on wind erosion. So at the time, I knew nothing. I knew zero about dust. But you probably remember in the year 1982 and 83, we had a very strong El Niño event, and the dust storms were very active in Australia, especially the 1983 dust storm event, the so-called Melbourne dust storm, has caught the attention of the public. And so a few scientists like Mike Ropak and John Lees and Grant McTunch and started thinking seriously about wind erosion. So I was probably the only full-time staff member in Australia to work on that topic. So it was really interesting. So one day, the Minister for Science, Rose Free, and came to the Pi Lab, That's where I work. And Mike Ropek and John Lees were busy to illustrate the wind erosion problem to him using the portable wind tunnel of John Lees. And then they put a fan in and start the model, but nothing came out of the wind tunnel. So that was we were in a panic, sort of. We couldn't generate wind erosion using wind tunnel. Then the idea of saltation bombardment came to the mind of Mike Ropek. So I'm sure Mike learned this from Dale Gillette about the saltation bombardment. And then we placed some sand in front of the dust pitch, as you can see from the graph, the upper part of this graph. So that's 1 meter sand and then 2 meter dust in the wind tunnel. And then we measured immediately, we generated a mini dust in that wind tunnel. So that is actually the origin of the idea we published in the paper Shao and others, 1993, the effect of saltation bombardment in treatment of dust by wind. By the way, this is actually the only paper I published without revision. We just sent in, so the journal said, okay, you can publish it. I was very happy. So a very important result came out from this experiment. Is illustrated by the graph here, the lower part, and that is the dust emission rate measured without saltation. So you have a lot of dust on the floor, and you switch the tunnel, the wind on. You increase wind speed to a very high level. At this stage, for example, here, 30 meters per second. And then you can see the dust emission quickly decreases to a very low level. So that is of dust emission limitation. Although you have a lot of dust, you cannot get the dust lifted. Based on that idea, the so-called saltation bombardment mechanism is formulated. And then we also developed the dust emission models based on that concept. But after so many years, dust emissions is still a big problem. So as you can see, here's a comparison of the dust emission estimates by the various global climate models participating in the CEMIC 6. So there are many studies on this topic, and this is a paper from Zhao and others, 2022. But you see the huge difference in the estimated dust emission. And some models say 1.5 teragram per year, while the other models say 7.5 teragrams per year. So this is still another issue is related to dust activities in a warmer climate. So we know we are having a global warming. Is the Earth getting dustier or less or cleaner? So Joe, based on MERA2 data, found that dust increased since the 80s, driven by the rising temperature in regions outside traditional dust source regions. Liang and Jasper Cork and others reported 50% rise of global dust emissions since pre-industrial times, and despite global warming. But then we analyzed the surface data, synoptic observations of dust storm events, and we found actually a trend of decreasing trend superimposed by variations. So that's still a lot of uncertainties. You probably also follow the debate. The global dust emission estimates seems to be a big problem. This estimate has been changing, actually increasing. Yeah. So the work Shao 2011, we summarized the literature and found the values were between 50 and 3,000 teragrams per year. Bauscher and others, then 1,000 to 4,000. Jasper Cork and others reported 5,000. Adrian is here, actually reported the dust emissions should be 2 orders of magnitude smaller. But Movad and others published another paper and disagree with our great Adrian. Yeah? So dust emission remains a major research topic, and one deficit of existing dust models capacity of modern source limited dust emission. Yeah. So now, what is the source limited dust emission? I'm sure everybody has a slightly different opinion. So therefore, when we started working on this problem, we thought, okay, we probably have to divide the source limited dust emission into different types. So I would like to call this source limited dust emission type 1. And for example, surface cover, soil moisture, surface crust, they all limit dust emission. Partly, these factors we have already considered in dust emission models by modeling the threshold friction velocity. So that is what I call the first type source limited dust emission. And the second type of dust emission is really about whether that can be emitted. Or you can probably interpret this in a slightly from a slightly different angle, and that is actually the binding characteristics of the soil particles. Yeah. So this graph shows the upper part, the particle size distribution. For example, before a dust event, that will be represented by this solid curve. After dust emission, part of the particles, small particles, is already lost. So you get a PDF, or the particle size distribution, represented by this dashed line. And then you probably have some renewal processes and the weathering processes, which then regenerate the dust particles for emission. So that is then by the thin solid line. So I would call this type of source limited dust emission, that source limited dust emission of the second kind. So the work we are doing is really about this part. But as you can see here, if you would like to deal with this problem, you would need to model dynamically the evolution of the soil particle size distribution with time. So there are quite a few models which can do this. One of the models we are developing here in the University of Cologne is the UOC dust scheme. So that is actually a summary of the old scheme. We started with giving the friction velocity, some soil particle size distributions, and the soil moisture, the frontal area index, and the surface cover, and then the theoretical threshold friction velocity. And then we do a lot of modifications according to the surface characteristics. Then we model the saltation, and then we model the dust emission, and finally we estimate the total dust emission. Now, by the way, this is actually a diagram summarized by Damianova and Sokolik, but this graph I've been using all the time also, and they summarized our scheme very nicely. Okay, so I would like to say a few words about the UOC dust scheme. So first, we consider the saltation bombardment and the aerodynamic entrainment. So these are the mechanisms we included in the UOC dust scheme. Now, we made some updates of the scheme by considering the intermittency of saltation of using directly the Bagnard oven type of saltation model. So in this case, we consider the shear stress as a stochastic variable, and also the threshold shear stress or the threshold frictional velocity as a stochastic variable. If you do that, you still apply the Bagnard oven type equation, but you need to integrate twice over the probability distributions of the threshold shear stress and the shear stress. Okay. Now, a major problem in these dust emission schemes is to take into account the dust binding strength. This is where the difficulty lies actually. So Beatrice and Jill have already paper on siltation bombardment efficiency. So the equation here we presented is nothing about siltation bombardment efficiency, but we have taken into account really the binding strength between the soil particles. Yeah, so that is what's really represented in this red brackets. So in this red brackets, there's a sigma p, which is the ratio of the so-called minimally dispersed particle size distribution and the fully particle size distribution. So I'm not sure whether this is a good idea or not, but we have been using this for a long time. The reason for us to use this is really to provide a constraint on the binding strength, the estimates of binding strength between the soil aggregate, between the soil particles. Of course, has another idea on the fragmentation of aggregates, but that is also a model for the binding strength between the soil particles. Stefan Alfaro has this Dutch emission and U-star relationship, which is also a very important sort of insight into the process. So now you see here the blue curve is the so-called minimally dispersed particle size distribution, and the red curve, with dots here, is the fully dispersed. Now this idea comes from Grant McTunch, so I learned from Grant McTunch and use that in this model as a constraint for the binding strength. Of course, there are problems. I stuck with Grant and the data sometimes not accurate, so not easy to get. So that has been also a disadvantage of the problem of the model. Okay, the other thing we did is to consider the turbulent dust emission, and that is mainly the work by Martina Klose, and she presented this wonderful graph on convective dust emission, which very nicely illustrates, even if you don't have a mean wind, but you have strong turbulence, you still can get dust emission. This graph also shows that the structure of turbulence is an important factor for dust emission. Now, I show you the data from Mikami and Masahide Ishizuka and John Lees. This is a graph plotted of streamwise sun drift against the U-star cube, and you see a big cloud. Okay, we know that data has inaccuracy, but if you study very carefully, then you realize that most of these points on top of this cloud are measured under convective conditions, while the dots here are mostly in stable conditions. So that means the structure of turbulence becomes an important issue for the dust emission. Okay? Please also say Kafala and Alfaro in 2020 about this issue. Now, siltation, what you said is very important. We said, okay, siltation bombardment, aggregate disintegration, all associated with siltation bombardment. But there seems to be another issue related to siltation bombardment and dust emission, and that's renewal. Huang Ling and Zhang Jie did a very nice wind tunnel experiment testing the 3 different soils in the tunnel: a natural soil, natural sand, plus natural soil and sift sand. So this is a larger picture. What you see here is that in this soil type 1, you have undisturbed natural soil containing dust and a larger clot, which prevents the siltation. Therefore, for a given wind speed, soil 1 has a relatively weaker siltation, while soil 2 and soil 3 has a stronger siltation. Now, if you compare the dust emission, I show here only soil 1 and soil 3, and then you see here, like we already observed in the 1993 paper, dust emission initially, and then quickly drops to a very low level. So a limited case of dust emission. And then if you have the soil 3, you can have fairly strong dust emission, which is maintained over a relatively long time period. So again, a source limiting case, but this one shows saturation has another effect, that is to generate, to make dust available for dust emission. Yeah, so more source limited case, less source limited case. So let's say something about the source limited dust model we have been working on. So here is the idea. We have a erodible soil with a erodible soil layer depth H. So let's suppose we know the PDF of that soil, then we know the of particle size in different dust size bins. That is this PI. So imagine in the deeper soil, you have a soil which might have more dust with or less dust. Anyway, you have a different particle size distribution. But if with the changing intensity of saltation, there will be some kind of mixing between these two layers. And for example, smaller particles can be mixed into the upper layer and therefore make the dust emission more dust susceptible to dust emission activity. Actually, we have done also a very detailed numerical simulation here in Cologne, which actually shows this this effect. But okay, so if I have a erodible soil depth H, then soil mass is M. Here, rho S is the bulk density, and H is the depth of this layer, and the fraction of the dust in this particle size bin is Mi, and the Pi is the mass fraction of bin I. So if you make this assumption, then don't consider any other processes. You only consider the emission and the mixing in the soil. You can estimate the change of particle size distribution with time using this equation. Obviously, if Pi 0 equal to Pi, and this will disappear, and then you find out that the particle size distribution, the mass, the fraction of particle size I or Di will eventually with time, given an emission at the surface. So that is then, so because of this emission at the surface, dust will be depleted from the first layer, and then there will be no dust available for dust emission. So therefore, you have the source limited dust emission of the second kind. Okay. So now, if you consider, so how deep is this erodible soil depth? So wind tunnel observations shows that okay, H needs to be proportional to the saltation intensity, the Q. So therefore, proportional to Q. And if you consider weathering process and other factors, you can estimate the change of dm, dt, proportional to mi, and plus some kind of source term, so external source like deposition, alluvia process, and the freezing, thawing process. If you consider what this process is, and then you can modify the equation I just showed earlier, that the change of the fraction here, Pi, you can estimate that using this expression here. This expression has basically four factors considered. One is, of course, saltation, which determines the mixing and the depth of the erodible soil. And what is the soil characteristics in the deep layer, and the strength of the emission, and of course the weathering and the other processes which we need to consider. So that is the equation we are using to model the change of available for emission. Yeah? So based on this, then we modified the University of Cologne dust scheme. So we started from here, like before. We added intermittency, convective dust emission from Martina, and then we ended up here. We added a dynamic particle size distribution module, and this goes back to the very beginning because this changes the particle size distribution, both minimally dispersed and fully dispersed. Then we conducted some theoretical experiments. I just used a constant wind speed with friction velocity 0.4 meters per second. Then you model the saltation, so that this is the Q, streamline centric, time, while the dust emission rate and the decreases with time because of the depletion of dust by dust emission. So as the soil becomes sandier, the saltation flux increases, and therefore the ratio between F and Q is by no means a constant. So it decreases with time. So this is actually also observed. Yeah, again, if you go back to the data by Ishizuka and Masahide and Mikami and others, you select a few events. For example, on day 61, you plot measured dust emission against measured streamline centric. You can see the ratio decreases with time. Clouds data, I just draw an arrow to indicate the decrease, and you can see very clearly that's a decrease. On day 71, you have another similar situation. Initially, you have a relatively strong emission, strong saltation bombardment efficiency, and then it decreases with time. Yeah? So that is what happens with particle size distribution. There are a number of curves. You start with the solid curve. The red one is fully dispersed, and the black one is minimally dispersed. And then 2 days later, you get those dashed lines, right? So you can see, especially in this part, the reduced fraction of dust available for emission. So there again, I used the J data to test. First, we plot the order of observations, and we calculate we model the saltation flux. This is the frictional velocity. So that is a comparison of the observed here and modeled here saltation flux. So you can see the model does quite well for most of the runs here, but there are some issues here. The model are not modeling very well for some cases. Okay, but I'm not discussing this in this talk. Okay, now I did 3 experiments. One is reference without source limited dust emission. That's the red one. That's the experiment 0. And then experiment 1 is dust depletion. And experiment 2 is the depletion plus renewal. What is plotted here, important is the lower part, the graph B, is the ratio of that F divided by F. So the dust emission for experiment 0 minus the dust emission for experiment 1 and divided by the dust emission for experiment 0. So what you can see here, the green one is the experiment 1 results. So that is the case if you have depletion without renewal. Now this is only about 20 days, 20 days time period. You can see the emission reduced by the end, you get to about 80% reduction to only 20% dust emission you can get from experiment 1. So if you have, of course, renewal, depending on the strength of the renewal, you have this yellow curve. And of course, with renewal, this ratio is smaller than for experiment 1. It is very interesting. I don't know whether you have noticed that some of the green dots go actually, during some events, go to very small values. So I enlarged this graph for the very end bit here. This is the famous two events we always use. A very, very strong event here, and followed by some weak event, a weak event. So you see here, there are a lot of dots, green dots here with very small values. So here, if strong saltation, then your edge will increase. Therefore, the available dust in the deeper soil layer becomes available, and therefore the difference between the runs without softening without dust emission and the runs with depletion becomes similar. So now, of course, this is also very, very clear if you consider renewal. Yeah? So in this place, you have an increased edge, and you also have an increased exchange of particles between the top soil layer and the deep soil layer. So that is why you get this kind of result. So this is again the real case, fully distribution, the red curve. The dashed one is at the end of the simulation, and the black one is the minimally dispersed particle size distribution, and the thin solid one is for experiment 1, and the dashed one is for experiment 2. Now, you probably have noticed in this example, the fully dispersed particle size distribution is not changing too much. There are some changes, but the changes are not so pronounced as the minimally dispersed. So this is because this aggregate disintegration only happens at a relatively strong wind speed. But in the JADA experiment, there are not many events with very strong wind speed. There are with strong wind events. So therefore, the fully dispersed particle size distribution didn't change so much in this case. Then I compared the dust emission estimated from the different experiments and then the observations. This is this graph in the middle is the very early section here, and this graph here in the bottom is this section here at the end of the simulation. Of course, initially there are no difference between those experiments because the particle size distributions are the same. But in the end of the simulation, as dust emission goes on during this 20 days, there are differences, actually quite large differences between experiment 0 and experiment 2. So here you have three curves. One is the observed, the red one, and this one here is experiment 1, so without the source limited dust emission, and experiment 0. Sorry. So experiment 1 is the green curve. The green curve. It is a little bit difficult to judge which one is better, but if you just look at this graph in the end, it seems the experiment 1 actually gives a better agreement with the J data. So that is actually all I want to report. I know it's a bit late, so that's these are my conclusions. We developed a model modeling the dynamic evolution of the soil particle size distribution by depletion, renewal, and weather. This is the so-called dust emission of the source limit dust emission of second kind. This has a very profound impact. Global dust models do not consider this. So maybe there are overestimates in the global dust emission. The other thing is the physics of dust emission seems to be much more complicated than we have thought before, because this renewal process really relates to the profile of the soil. For example, gourmet dust emission quickly reduces to zero due to source limit dust emission. But farmland dust emission lasts longer at the potential level. Yeah? So a referee of our paper summarized our results very nicely. She or he said, dust emission is a competing process of depletion and renewal. Global dust emission may be limited by renewal. So that's my talk. Thanks for listening. I look forward to discussing.
Wonderful. Thank you very much. I see a lot of clapping emojis. Everyone, please feel free to type questions in the chat. I'll also just keep an eye on the participants if you just want to raise your hand or ask to unmute to ask your question directly. Philippe, do you want to take the first question we have from Daniel?
Yes, we have a question from Daniel Bellamy. So the question is, how deep is the topsoil level for the depletion calculation?
Yeah, I mean, the erodible soil layer, we have only a few millimeters. Yeah, and then this will help us to determine the ratio between the saltation flux and this edge. And so a saltation flux increases, and this edge will slightly increase. But it's a order of magnitude of a millimeter.
All right.
Yeah, JB.
JB has a question.
Yeah, I thought maybe I asked my question instead of typing it. Thanks, Yaping, for your presentation. Now, I could not help notice that in the first few slides you make a distinction between sand and dust. I think this is grain size related, and but in the end you emit dust, or you emit aerosols of medium and maybe even larger size fractions well into the sand fraction. Has this is this an evolution through time that the coarser particles may be emitted by the models, and could it maybe also be
in this model, sand is not that does not have a netto vertical flux, but in our model we have aggregate disintegration. So much of the disintegrated particles are actually in that size range. So you do have a particle size sort of change also in the size range, let's say 60, 100 microns.
Okay.
Is that, yeah, because of the disintegration actually.
Yeah, I was wondering, could this be a reason, but maybe Adrian would like to comment on this as well, why the models differ so much in the amounts?
Oh, you mean in the same six comparison?
Yep.
Oh yeah, I mean that is one thing as a community we have to decide to actually define what is the dust. Of course, the dust is dynamic. It depends on U star. If you have a large U star, your dust particle size will increase with the boundary, I mean, dividing dust at the same. But I also know you are working on large particles, so that's because the structure of the turbulence. I mean, if you have in the end of the turbulence sort of distribution, very, very large burst, and then your large particles becomes a dust.
Yeah.
So everything is relative. So we need a
All right, thanks. Adrian, would you like to ask your question? Maybe you can switch on your camera as well so we can see you, actually. If it's really you. It is you. Good to see you. Please
And
shoot.
you. Yaping, really enjoyed the talk. It's great to hear that you know, these really important topics are being tackled 20, 30 years after the development of some of the original models. Your description reminded me of a process in sedimentology. There's a paper around about 1990 by Saran Chansey, and it describes how particle sizes on a dune can be separated due to the bombardment. And what they found is that different places on the dune where there are more or less bombardment had different particle size. Now, that's not just because of the movement, it's because of a shaking mechanism. So when you take a mixture of material and you shake it, coarse material comes to the surface. So if you were to consider your subsurface with coarse particles and your top soil with fine particles being bombarded, I wonder if maybe a term missing in the model is the ability to actually bring those coarse particles up to the surface, which would then reduce the dust emission and might actually explain some of the particle size distributions that you find. I mean, it's kind of experimentally based.
Excellent idea, Adrian. One of the stuff which is troubling us is that we don't have so many experiments done on this issue. Zhang Jie and Huang Ling in the London University, they're actually planning some well-designed experiments on this issue. So once we got this data, we would of course take the idea you mentioned into consideration. But I'm not sure whether this is really shaping like a seed when the ocean events. But it can be that the Southeast bombardment can actually bring some large particles to the surface. But this might be the case for the Gordy. We don't know. So we'll find out. Good point.
Questions from other people? Don't be shy.
Martina,
Yes.
please.
Thanks again also for me, Yaping, for the very nice presentation. Yeah, you mainly showed your comparison of your results against the JADE data set, but in the end you also mentioned that Gobi dust was reducing to zero really quickly. So I was wondering, did you test this for other soils as well? Do they behave in the same way, or perhaps the renewal mechanisms may differ? And perhaps in a similar sense like before, perhaps from your wind tunnel experiments, there is a way to somehow verify the the availability of dust from the soil after it's been emitted.
No, I didn't test any with other data set. I think the importance of this paper, if any, is really to illustrate this problem and how this problem can be somehow theoretically modeled. There are some parameters we have to tune, of course. The thing is, Masahide and people are prepared with wonderful data set, which has all the parameters you need to test, while many other data sets do not have this kind of completeness. So anyway, okay, the short answer is I haven't done that yet. So, but I hope the Aeolian research community can design some kind of experiment and model comparison more dedicated to this problem, because I think this is really a big challenge. I mean, we have been working, Adrian has been working on this for 30 years. He has many new ideas, but this seems to be an area focus. Yeah, basically no.
Right. Any more questions?
Well, if not, let's again thank you, Yaping, for such a wonderful talk.
Thank you very much. Thank you
Yeah.
very much. Thank you.
We have just a few quick reminders before we wrap up. Again, these talks are recorded, so please head to our website and you can watch them again once they're posted, a few days up to a week after the talks. We encourage everyone to make sure you're keeping up on your ISAR membership. By doing that, you're making sure that you're receiving our community updates, such as our quarterly newsletters. Our June newsletter is coming out soon, which will include updates for the 2026 ISAR award session. We actually have some new awards coming out. The board has been hard at work at introducing. With it, if you ever have any questions, you can always reach us at admin@aeolianresearch.com. This is on our website also. We have one more talk after this from Chloe Dudon, and I don't have the date pulled up in front of me. Apologies. July
22nd.
22nd. Great. So make sure you're signing up for Chloe's talk.
No, 23rd, right? Let me check again. 23rd. Well, no, 22nd. 22nd.
So if you head to our website, you can find the Zoom. You'll find the Zoom link to sign up for Chloe's talk. And that is all I have. Thank you all so much for joining us today, and thank you, Yaping, and congratulations on your award again.
Thank you.
Yeah, thank you. Very nice to see so many friends here, and I hope to catch up with you another occasion. Yeah. Thanks.
ICAR, even though it's backwards. Sorry. Hopefully we can see many of you at ICAR next summer. All right.
Oh, yeah. Jan Baron, when is this birthday? Have you seen things around?
Yeah, it's 6-7 November, right? Martina, Kerstin, did you
I
please
believe
confirm?
so, yes.
I think so, huh? Yeah. It will be in the newsletter too.
I can forward the email to you. Yeah.
Okay,
Yes.
thank you. Okay.
Good seeing everyone.
Do you want to end the recording?
Okay,
You
bye.
can do that, yes. Good idea.
Thank you.
How's everything else going? Adrian.